Thank you all for coming. If you are interested in slides for whatever reason, if you have difficulty seeing, you can either hit that QR code or that short URL. But yes, today we're talking about explaining what the heck edge compute is. Hopefully you all have heard of it, maybe in passing, maybe you have some experience with it. I'm going to talk about what it is, what it's good for, what it's not good for, when it makes sense, and some use cases. So a little bit about myself. Yes, I've been building websites since 2013, and I mostly consider myself a development educator at this point. I work for a company called Akamai. We are the most distributed CDN in the world. We offer edge compute, but my role is more intended not on selling people on the products that we have, but educating people so that you can make the best decision for building your applications. I also have a really cute Chewini named Nugget. That's him right there, but yeah. So just plain and simple, to get it out of the way, edge compute is the result of distributing serverless functions to multiple locations all over the world to handle requests from users from as close to the user as possible. And the benefit or the result of doing things this way is we have a way to create programmatic or dynamic or customizable responses with the least amount of latency. Latency being the amount of time that a request and response has to travel in flight, not actually doing any work, to go from the client to the origin server or to the server and back to the client. So it's basically related to speed. So that's it. If you just wanted to understand what edge compute is, there's another wonderful talk that I will not hold it against you if you want to go and listen to the other talk that's going on. But I also think that there's more to say about it, and that's a really boring explanation. So we're going to talk about it in a more exciting way by comparing it to knitting hats for dogs. So when we make hats for dogs, the natural progression is you have a client or a customer that wants the thing, which is the dog hat. They request it from you. You spend some time and energy and work making the thing, and then you give it back to them. And it makes for really just a mediocre analogy, but for some really excellent photos. So that's what we're going with. So the first thing when we talk about edge compute, I like to break it down and talk about the two different parts. We start with compute first, and that is essentially the computer doing some sort of bleeps and bloops or doing some sort of work to produce an output. In our case, we compared it to knitting the hat for the dog, and the output is the hat. In many cases, that's going to be HTML. It could be programmatically generating images or JSON or CSVs or something like that, but we'll keep it simple and just talk about HTML, right? Computer does some work, output is HTML. And where that work happens is more interesting because we have things like traditional servers, client-side rendering, which can be either in JavaScript or WASM. You have static site generators, you have cloud functions, and then we have edge functions. So we're going to look at kind of each of these and get a better understanding to paint a more complete picture where edge compute fits in across all of these compute options. So with traditional servers, these are essentially machines that you may rent from a cloud provider or you may own and have on-premise, but they essentially, you're managing the software that is running on that machine as well as the software that runs your business logic. So the benefits of traditional servers is you have things like predictable pricing where you show up and you say, I'm going to pay $5 a month or $70 a month and get the same resources. The benefits of traditional servers is you are in complete control. If you have special needs or use cases for specialized programming languages, you can install that on your server because you control what that server contains. You also have access to unbounded runtimes. So if you have long-running processes or cron jobs, these are things that are good for traditional servers that other runtimes can't necessarily support. But there's also downsides to traditional servers, and that is because you have these unbounded runtimes and you pay for having access to it 24/7, you may pay for time that is not being used. So if you have a sort of business that the work is being done 8 hours a day during normal business hours and everyone goes home and no one's using those servers, you are still paying for that time. They also can be challenging to scale because you might have one instance, and then to have more compute, you either need to upgrade the resources on that server or add additional servers. And these servers, whether you are provisioning them in a building that you own, or whether you're using a cloud service provider, you're generally deciding on a specific location that that server is going to exist, which means if users in Berlin want to come to my website and I have my server hosted on the west coast of the United States, that's a long time that that request has to travel to the server and back. So you have more latency issues. And although being in complete control is a benefit, it also comes at a cost because you are the one that's responsible for maintaining that server. So similar to traditional servers, I like to think of them sort of like in the dog hat knitting business, like a commercial workspace, right? You may own the building, you may rent the building, but ultimately you have access to that building 24/7, but you're sort of responsible for maintaining it, and you are paying for the utilities and basically keeping that space for your work. Next, we have client-side rendering. So this is where we have either JavaScript or something like WebAssembly that's going to do the compute on the user's device, and it's going to generate the HTML for us. So think of you click a button on the user's device, some JavaScript runs, creates a button element, appends it to the page, things like that. The nice thing about client-side rendering is the user can make a request to get the resources and essentially the rules or the JavaScript that designs the application, and once they have that downloaded, they are no longer experiencing latency between clicking the button and that compute running, so that they're not making an HTTP request to a server in a distant region, right? It's already on the device. With certain things like progressive web apps, you can also run this client-side rendering logic offline, so user can make the initial download and then take that somewhere offline if they need to. But the problems with that is, notice that in the first request, the user has to download some extra JavaScript for that, to have the logic on their device in order to know what to do. Now, that comes at a cost to the user, right? It's not a cost for us, but we're asking them to download more data, which means that that might affect how much they pay for their phone plan or something like that. There's also no way to keep secrets if you're relying just on client-side rendering. So if you have some API keys or tokens or things like that, you can't put those in client-side only rendering and expect them to be kept private, because any tech-savvy user can right-click, inspect element, see the source code of the page, and according to the US government, that's like hacking a website even though it's right there. Let's not talk about the US government. So the other challenge with client-side rendering is where with traditional servers, you have control over the environment because you choose the software on there. When you expect the client to render the page, they're in charge of the environment. They might be running Chrome, Firefox, Opera, or any of the different browsers, right? And so we as application developers have to be aware not of the environment that we control, but we have to be aware of the potential environments that our application could be running in. And because all of this is running on the user's device, the performance of our application is directly related to how well their device runs. If they have an old device or they have a lot of different processes running, our application is going to run slower. And conversely, if our application is very heavy, it's going to be a cost on the user because it could be using a lot of the resources that they could be using for Candy Crush or something like that. So I like to think of client-side rendering sort of like a do-it-yourself dog hat knitting kit, right? The user might come to our store and buy the kit and take it home with them, but the actual work that has to be done is on them. So we might provide the yarn and the knitting needles and the instructions, but they're the ones that's doing the actual work. Make sense? Okay. Next, we can talk about static site generators. Static site generators are essentially where you have a machine that's going to generate all of the pages for your website ahead of time and then put them into static folders. This is really handy because it's a way that when a user makes a request for the pages, they're no longer, all of the work has already been done ahead of time. So they make a request, the server is just going to find the static HTML pages and JavaScript and CSS and return it, and it's a lot faster. It also works really well with CDNs, which we will talk about in a moment. And this type of hosting can be fast, cheap, secure, and really easy to deploy. But the biggest problem with it is we can't deal with dynamic data, at least not unless we also introduce client-side rendering. But essentially, when we're building everything in advance, we don't know who the user is that's going to request that page, so we have to build just general purpose or risk exposing things that we should not be exposing. So you generally don't want to use dynamic data when using static site generators. Again, this is if you're not including client-side rendering as an additional overhead. And one of the big problems with static site generators is as you have more pages in your application, the build times for all those pages grow linearly. So eventually you might run into a website that's too large and cannot actually build in that short amount of time. So I like to think of static site generators as having a collection of pre-knitted dog hats. So users can come to our store now, or clients can come to our store, and we can build, or we can knit out the most popular sizes for breeds, for colors, or things like that, and just have them ready to go so someone doesn't have to come in and tell us what they want and wait for us to finish knitting them. That work can already be done ahead of time, and they can just grab what they need and go. And then the last sort of introductory compute is Cloud Functions. These are also sometimes referred to as Lambda functions or serverless, and this is essentially where you have a service provider that is going to be responsible for routing traffic to an endpoint that they provide to you, and they run a function that you provide to them. So the nice thing about Cloud Functions is that they're very easy to provision. So if you have teams or migrations, you can deploy a new Cloud Function and sort of start sending traffic to that incrementally. And you can have teams that are responsible for their individual Cloud Functions without having to have some sort of big monolithic application. They also follow this concept of being infinitely scalable because of the way that they are provisioned. The cloud service provider can essentially route more traffic to more computers that are running the same function that you provide without necessarily you having to worry about adding new computers and scaling it. They'll do it for you. And in theory, it's infinitely scalable, although not technically infinite. The other nice thing about Cloud Functions is you pay for what you use. So compared to the traditional servers, if you're only running your application or your business only runs 8 hours a day during business hours, the other 16 hours of the day, you're not paying for that. So that's pretty nice. And once again, because you're only providing the functions to the service providers and they are responsible for the deployment and the scaling and the routing and the networking, the scope of work that you have to be responsible for and aware of is just the business logic. So you don't have to worry about maintenance on servers. Downsides of Cloud Functions is you do have to follow much more strict conventions of what the service providers offer. So they get to decide what programming languages are available. They get to decide how many resources can be allocated to a Cloud Function or what the maximum limit of resources in terms of memory or bounded times, the duration of time that the functions can run. They also follow this concept of being stateless, which means in order for them to be scalable and run across multiple devices, you cannot have access to a shared system of memory or file system because you have no idea whether after the first request, the next request will be run on that same machine, which means you don't have access to the same memory. And once again, when you deploy a Cloud Function, similar to a traditional server, you are going to be selecting a region in the world where that Cloud Function is going to be deployed, which means if users try to execute that Cloud Function from a different region, they have to take a longer time to, there's more latency time. So I like to think of Cloud Functions as, there's not really a very simple analogy or an emoji for it, so I like to think of it sort of as like dog hat knitting robots. So imagine there's a company that can provide robots that you tell them what the instructions are, and then you just have access to these robots. That's essentially what it is, right? So now instead of users that only get, compared to like static sites, everything built in advance. Clients can come and say, I have a very specific dog with a funny shaped head who also really likes the Patriots for some reason. And the robots can sort of take the spec of the dog and do the dynamic dog hat, which is great. Okay, so that's all I'm going to cover about compute. Are there any questions about that so far? Is that kind of a good rundown? Cool, glad. Now we're going to focus on the edge side of things. So edge can mean a lot of different things. I like to describe it as a network of globally distributed computers capable of handling user requests. And the reason why edge is important is because by putting resources as close to the users as possible, we can reduce the latency, thereby improving performance and user experience. But there's a question that comes up, which is how many locations qualify as edge? Is it number 2, where maybe it's you and your friend across the world? Probably not. But a lot of companies that do describe their edge do so with 10 locations or 100 locations or 300 locations or around 4,000. And then you can get into the tens of thousands if you're also describing things like IoT devices. We're not going to be focusing on IoT because I'm a web developer, and so I like to communicate in concepts that are related to the web. And the most relevant example of edge when talking about the web is a content delivery network, or a CDN. So this is, once again, several globally distributed servers that deliver static content to users. And CDNs are awesome because, once again, essentially, if we have different users in Tokyo or Toledo or Topeka or Toronto, they can all receive static assets with the least amount of latency because we can have locations in that CDN in all of those cities. So this can greatly reduce latency, and it also works really well with the compute options like client-side rendering or static site generation, because once again, we can build those assets in advance and then distribute those resources to the different CDN nodes around the world. The problem with CDNs, of course, is the same problem with the static compute options, in that we can't use dynamic content. So I like to think of CDNs as sort of like a convenience store, where in a previous model we had a single store where users would have to come across town to come and buy our dog hats. Now we can partner with a bunch of convenience stores, maybe think like 7-Eleven, and we can take all of the dog hats that we have, the dog hats and the dog knitting kits, and we can distribute them to these convenience stores. So now instead of traveling across town, people just can walk down to the end of their street and get the things they need from the nearest location. Okay, so all of that kind of compute and edge defined, I like to take a moment to talk about performance, because this is going to be the most relevant subject when talking about edge compute. And I like to say that users experience performance in 3D. That is, number 1, the distance that a request and response have to travel. This is also referred to as latency. Number 2, the download, which is the amount of data or resources that users have to download in order for that program to be executed. And number 3 is the device, so the capabilities that their device has in order to run that application. This isn't probably the best choice of words, but I find that alliteration is supposed to be good when giving presentations, so that's what I went with. And that brings us to what I like to call the speed of light problem, which is that despite the fact that technology continues to advance and users' devices get faster and faster, eventually that will solve a lot of the speed problems that we have, but we're always going to have the problem of the speed of light. Unless we can come up with wormhole technology and fold space and time, then even though devices are going to get faster, the speed of light will remain a constant and will remain the same. So if we have a user that is making a request to an edge node that's very short or very close, that amount of time is going to be much faster than if they have to go a long way. And yes, I use distance as time. It's very clever. So with everything in mind, with all of that we've discussed, the ideal scenario for performance is to do things as close to the user as possible so that we reduce latency, like a CDN, and we move more of the work onto the servers because, as we've seen, users' devices are not as reliable for providing the best performance. And so moving things to the server is going to support compute options like cloud servers or cloud functions. And we probably want to send smaller assets. This one, I don't really have a solution for because it's so subjective to whatever your business is or whatever application is you're building. But follow best practices in reducing sizes. But with that in mind, we can say that the logical next step is to naturally put those dog hat knitting robots inside of the convenience stores. And that's essentially what edge compute is. We end up with programmable runtimes, like the cloud functions that we discussed, but they're also globally distributed, like a CDN. And they end up, where they live in the sort of application is between the client's device and an origin server, which would be like those traditional servers. And the benefit that we get from edge compute is dynamic server-side functionality, like cloud functions, but they execute as close to the user as possible, so they reduce latency. In addition, a couple of bonuses to edge compute is you generally have reliable location for where that edge node is. So this adds a little bit of an interesting paradigm shift from a traditional server, because when you deploy a traditional server, you decide where that's going to be deployed to, so you already know where it is, but it doesn't tell you anything about where the user is. Whereas when you have location information from the edge node, you have some pseudo information about where the user is making the request from. And most edge compute providers also give access to some data storage in a rudimentary key value store. So not necessarily something like SQL, but very useful for some of the use cases that we'll see. So for users, this is a good thing. Edge compute is great because they now have access, once again, to that dynamic content, which is more interesting than static. But they also get that with less latency because they don't have to wait, if you compare it to a traditional server or a cloud function, they don't have to wait for it to travel theoretically around the world and then back. They also have less that they have to download onto their device when you compare it to something like client-side rendering. And they have less work to do on their device, which can be better for their battery life, the performance of other software running on their device, and once again, they can continue using Candy Crush. This is also good for developers because it introduces, similar to cloud functions, a low barrier to proof of concept. Because once again, edge compute is very similar to serverless, or I would even consider it a subset of serverless functions, where you don't have to be responsible for provisioning servers. All you have to do is write the business logic and deploy it to the service provider, and that allows you to create more iterative functions more quickly, whether you're doing different teams are responsible for different business logic or migrating different services. This also gives you a consistent execution environment, so you don't have to deal with the cross-browser issues that we sort of discussed about client-side rendering. We talked about the location-based logic that you can introduce, which can be useful for a number of different things. And because we are running on a server side, we have access to creating applications that have secrets, so secret keys, API tokens, things like that, that cannot be viewed from the user's device with view source, unless they hack it, which you probably have a bigger problem. Also, most of the edge computing providers use the most popular programming language in the world, which is JavaScript. So that means you have something that hopefully your team is familiar with. You don't have to work on some very bespoke and esoteric programming language. And once again, because the service provider is responsible for taking your code and deploying it and scaling it and handling all the network, you don't have to deal with the server infrastructure or maintenance. So that's the benefits for developers, but we also can look at benefits for website owners. Because we can move the compute to different edge nodes rather than running some of that logic on origin servers, we can reduce the load that ultimately has to run on those origin servers, which can, one, either improve the performance of the work that's being done on the origin server, or you can improve the reliability because it's not going to be as easy to consume all of those resources. Or if you see that you've moved a lot of the work off of the origin and into the edge nodes, then you can actually consider reducing the cost of the origin server because you can downgrade the sort of resources or the tier that server might need. It's also nice to have automatic scaling, so similar to the cloud functions that we discuss, edge functions follow the concept of being infinitely scalable, so you don't have much to think about, and as a website owner, this is a great thing because you don't have to worry about your servers potentially falling over when there's a big spike in traffic. And it also follows the serverless sort of model of pay for what you use. And keep in mind that some of the things that I say are mostly general across different service providers. I won't speak to anyone individually unless I say so explicitly. But yeah, most of them follow the concept of you pay for what you use. Edge compute is not perfect though. There are some rough edges, wink, wink. So for example, similar to cloud functions where you have a limit on the resources and the programming languages available, edge compute, most edge providers, or at least up until recently, most of them, didn't use something like Node.js at the edge because Node is a much larger runtime, and if we're talking about deploying functions to 4,000 locations around the world, you want those to be as fast to boot up as possible and as lightweight, because otherwise it's going to be a major cost on the provider. So rather than doing things like deploying Node.js at the edge, you have what are called V8 isolates, which is essentially the JavaScript language with a much more smaller footprint and only access to very limited platform APIs. So things like, and some things don't make sense, like with Node. You don't want to write to the file system in a system that may not exist there the next time it runs. You also have generally like limited compute resources. So where on a traditional server you have unbounded resources in time and you have whatever resources you pay for. Cloud functions, you have much more limited options for resources. Edge functions, you have even more limited. So in terms of the amount of time that a function can execute, it can be something like in the hundreds of milliseconds or very low seconds. Also, the amount of memory that is available in these runtimes is much more limited. And we talked about time resources already. And one of the most interesting things that when I was first learning about edge compute that they don't talk about is the limited networking protocols. So almost all of them support HTTP, but support for HTTP does not mean they support TCP over IP. And this is very relevant because when I first heard about edge compute, I said, cool, let's move an application from some central server to edge node and run my app there. Problem is, if your application has to talk to a database, database connections generally happen over TCP over IP. So if you want to support talking to a database, you'd probably have to set up some sort of proxy service in front of a database that can communicate over HTTP and talk to that proxy service first. Now, considering that that's one of the hard things, a lot of the edge compute advocates like to look at the rainbows and unicorns, but don't like to talk about the thing that's actually really hard. Distributing an application globally around the world is not the hard part. Distributing data around the world is the hard part. So I like to compare this to different examples that we can look at, where I have a little key here that shows the computer is going to be the client or the user. The guy in the tuxedo kind of looks like a server, so that represents the origin server. The knife has an edge, so that's going to be the edge node. And then the target is going to be some target that you want to communicate with. So where you might have an origin server, an edge node is going to sit between the client request and some target service. Might be a third-party API, it might be that database proxy. So in some cases, worst case scenario, this is what these are going to represent, where the line represents the amount of time between those requests. If you look at a traditional server and you have a client that makes a request to a service where the server exists in the same region as the target, worst case scenario is a very long request to the server and then a very short hop from the server to the target. If you compare that to an edge node, it's roughly the same because now the user is going to make a very short request to the edge node. It's going to be as close to the user as possible, right? And the worst case scenario is the edge node has to make a long request to the target service. So pretty much the same, not a lot to win or lose there. If we compare that to a service that's in a distant region from the server, you could imagine a scenario where, let's take Berlin and Portland as an example. We have users in Berlin that want to go to my website. My website or my application is hosted in Portland, Oregon, so that's a long way for that to travel. But then if the service that my server sits in front of and has to communicate is also somewhere far away, then all of a sudden we have a couple of long distances to travel. Whereas with an edge node, the user is always going to go to a location that's very close to the user, and then the furthest it can be is halfway around the world. So we have a possible win by using edge compute in an example like that. You can also do multiple concurrent requests. So think of something like an API proxy, where a user makes a request to just one compute service, either a server or an edge node, and then that has to fan out to multiple different services. Worst case scenario with a traditional server is the user is far away from the server, and the server might talk to some service that's close, some that's kind of close, one that's kind of far. Overall, it might be further for that whole request time. Compared to the edge node, the service, it really is just dependent on the furthest location from the edge node. All of this makes sense? Hopefully the distance of lines is pretty clear. Now that's great for that is great for concurrent requests, but if we're talking about sequential requests, now you can get into a really bad scenario by choosing edge compute. Because with sequential requests, you might have a server or a client that talks to a server, and then let's say if it's we want to do something like look up, grab a blog post, and then from that blog post, grab the categories off that, and then grab related blog posts or something like that. The service or the server might talk to that database proxy a number of times, but because they live potentially next to each other, there's a short time for that back and forth to happen. Whereas if we talk about an edge compute, that might have to travel a long distance to get to in this case, let's call it a database proxy, and then that has to go a long way back to the edge node, which then has to go and get got the blog post in the first request, had to go and get the categories in the second request, and you can see it just kind of takes a very long time. So, is this working? So the good news about the distributed data is that there are solutions. You can do things like move some of that data into the key value stores that we discussed that are available in these edge compute platforms. You can use something like replica databases. So instead of having a single data store in the world, you can have like a Postgres instance that is one that you write to, and then that can fan or duplicate that data out to different Postgres nodes around the world for just reads. Or you can use something like a distributed caching system like Redis. So the best way that I like to recommend people consider edge compute is not as a replacement, but more as an addition to the options of choices for where we can run compute, because where that is a tough question to answer, it just kind of becomes more difficult, because before we had things like client-side rendering, service workers, cloud functions, traditional servers. Now we're basically slotting in as another consideration edge compute, and I like to think about it sitting somewhere between client-side rendering and server-side rendering, because that is sort of physically where it exists in the stack. So today, or my first impression when I learned about edge compute was, great, I'm going to move my entire application onto the edge. And I think that after a lot of time and research, I probably wouldn't consider it for full-on applications today. But it's still good at other things. So at Akamai, some of the most common use cases that we see with our customers are modifying requests and responses in flight. So you can think of something like server-side ads that are injected based on a user's location. You could inject ads just on the client side using a script, but if your company or if your product depends on advertisement, those are very commonly blocked by ad blockers. If you can inject those at the server side, you can make it more difficult to ad blockers to block them. Also things like fast static search. So think of a scenario where you have a company that has multiple locations around the world. You can deploy some sort of autocomplete or type ahead sort of feature for finding those store locations, where because that data doesn't change very frequently, anytime that you have a new store location, you can update the edge key value store, and then when a user does a search, they can do a search, they can make that request to an edge node very close to where they are, very short latency, but then the work is actually going to process at the edge node and come back with the list of potential store locations, rather than running that compute on their device, or rather than making a long request to an origin server for that. Also things like geolocation. If you have something to deal with language or geopolitical policies, because you have access to the users, because you have access to the nearest edge node to where the user exists, you can do some logic around that without necessarily having to request permission from the user. So especially in Europe, this is relevant for things like GDPR, because you can pull geolocation from the edge node and not necessarily the user. You don't necessarily need to I'm going to be careful with what I say because I'm not an expert. I'm not a lawyer and I'm not a GDPR expert. But it is fascinating to do compute or some logic based on location when that location is on the edge node and not necessarily the user. I also wrote a blog post on something that we discovered around redirect management. So if you consider a traditional server like Nginx or Apache, if you have a couple of redirects that you have to create, you can write those into the server's logic. But when you get to customer sizes that have to migrate 1 million pages and you have 1 million redirects, that can actually affect the performance of that server just looking up the redirects or parsing the redirects rules. So there's a way to potentially store redirect logic inside of key value stores and use edge compute to manage those redirects so that when a request comes in, if it knows it needs to be redirected, it can be a lot faster to look up over very large quantities of redirects. Also things like token-based personalization, A/B testing, feature flags. You can do this at the edge and basically turn things on or off and rewrite the HTML. Doing stateless auth, so if you have something like JSON web tokens, when a request comes in, you can parse that token and see if the user has access to the resource that they're trying to request. Using an API proxy, so once again, similar to the example that we saw, where a request comes in and it fans out to multiple services, rather than those multiple requests happening either on the client side or at an origin server, you can do that at the edge. So it's all really exciting. I do think that edge compute is going to be a relevant part of the sort of next phase of web development. And we can see that it's not just me talking about it. These are a lot of the very popular frameworks coming out that all are either natively supporting edge as a deployment target or have some sort of adapter. And more are coming. So it's very exciting, but also it puts me in a position of feeling a little bit of existential crisis because at the end of the day, we're talking about a lot of work, a lot of architectural overhead, a lot of things to consider when really I asked some of my colleagues and they said probably you stand a gain on, worst case scenario about like 300 milliseconds, which to a human is, like now, like not a lot of time in human experience. But it does add up, especially if you consider how a web page loads and you have render blocking resources. So if you have the HTML being parsed and runs into some CSS file, and that CSS file has 300 milliseconds of delay before it can come back, and then the browser can continue parsing the page, those can add up, right? And anytime that anyone talks about performance, you have to include what I call the compulsory slide with lots of stats, which I don't think we need to read through. I put it up there because it's just a lot of text that basically says, or you can take a photo if you want, or the slides will be available online. But essentially, in 2017, so a little bit old now, Akamai did some research on retail performance and basically said that, yeah, there's a surprising amount of drop-off or surprising amount of impact that even 100 milliseconds has on conversion rates. So I like to, instead of looking at those stats, I like to provide a visualization example. Again, this is a little bit old, but it is an example that is often cited, that in 2008, Amazon found that a 100 millisecond delay hurt sales by 1%. And I think last year they had a revenue of $514 billion. So if you take the 1% of that, that's about $5 billion that 100 millisecond could theoretically be responsible for. Now, if you compare that to the average salary of web developers in 2023 of $83,000 a year, they could hire 60,000 developers. And if any one or all of them somehow managed to shave off 100 milliseconds, those 60,000 developers, Amazon would still make a profit from hiring them, that number of people, which is insane. And if you're interested in these sorts of stats or you want to bring this sort of information to your boss or company, there's a great website called wpostats.com. I'm not affiliated. I just found a lot of the stats that I used in this talk for that. So the real question that I imagine people are asking themselves are, is it worth it? And the good news is there's a very short answer. It depends. It's the most annoying answer that we always get in this industry. But I hope that when you need it, so I think the truth is, I don't think edge compute is right for most projects, but I think for the companies that are really at this scale, that 100 milliseconds is going to be a big issue, then it can be very effective. And I hope that you do give Akamai Edge Workers a try, because there are some things that make Akamai unique. We have, once again, it's the most distributed CDN in the world and edge compute platform in the world as well, with 300,000 servers, over 4,000 locations. There's also an interesting option for the different lifecycle hooks that you can tap into. So if you remember, I mentioned that edge compute runs in between the client and the server. With Akamai Edge Workers, you can tap into before the client request comes in, before it's sent to the origin, after it comes back, after the response comes back from the origin, and before it's sent back to the client. It also integrates well with Akamai CDN, which is industry leading in security and all these other things. But yeah, I will say that the key takeaways, the most important thing for everyone to focus on is that, once again, these distributed systems are very difficult to build and think about and architect. And edge compute doesn't make it any easier. In fact, it adds another layer of complexity when you're considering where you're going to run that compute. So once again, many projects probably will not benefit from edge compute necessarily, or at least the trade-off will not be worth it, unless they need to be distributed. But the important thing for the folks in this room, the reason why you're here, is because I think that it's a benefit, whether you're going to use edge compute or not, it's a benefit to understand it, understand those distributed systems, and think about your application and building them in such a way that today you may run your app on a single server in the cloud. And tomorrow you may want to distribute that to or introduce cloud functions, and a week from now you may want to introduce edge compute. And the most important thing for us to do when building these applications is think about not necessarily going straight to the edge today, but building our applications in such a way that we don't paint ourselves into a corner and make it more difficult to make that migration tomorrow. So definitely thinking about distributed systems first, even if you're going to be building just on a single server. And that's it. So I just am going to go through a couple of nice pictures of cute dogs wearing cute hats, and I'll get to my last slide here in a moment. There it is. Okay, here's some information that I have up. If you enjoyed this talk, or if you want to tell me how I can do better, let me know. That's just a link to that pre-filled a tweet for you. I do work for Akamai. We last year acquired Linode, if you're familiar. So if you want $100 in Linode credits, you can go to linode.com/AustinGuild. If you're a new user, that will give you $100 credit. And I am here to talk to people. I'm here to educate people, but also make new connections and make friends and talk about whatever. So you can find me at all these places. I'll be out and around. Please do come talk to me. I'd love to talk to you. And I'll leave that up while we take questions, if there are any.
So thank you very much, Austin Jill.